Okay, our theme for this first week of the class is Einstein in context, as we've talked about before. So what we want to do in this clip, and don't be overwhelmed by all the writing on the board here. We're going to go through it, and there's a handout as well on this. But we want to look at physics and Einstein circa 1900. Essentially look at what was the scientific and technological environment that Einstein was born into, and especially what was going on during the roughly 100 years preceding him that led into, in many ways, that influenced his work on the special theory of relativity. And we're just going to be hitting the high points here, pointing out some key things. There is, as I mentioned, a handout that lists all these and more details, and actually more than just the trends and events that we've listed here. In terms of the weekly review quiz, what you'll need to know are just the things we'll be talking about here as we work our way through it. So first of all, just what I didn't put on here, but starting around 1800, that's actually a good place to start in terms of physics, because even though the word physicist wasn't coined until about 1840, before that, people who worked in physics might be called natural philosophers. But around about 1800, you had sort of a split in terms of what people who were working on physics actually dealt with. They dealt with things like energy and matter, but up until, well, certainly through the 1700s, that could mean that you were also looking at organic examples of that in the animal and plant world versus also inorganic. But about 1800, you had a split start to occur, or sort of started before that, but would be occurring about 1800, so that physics came to be that branch of science that focused on matter and energy, especially in terms of inorganic phenomena. So actually the battery, invented in 1800, is a good example of that. And by the way, the dates here are fairly approximate. Some of these go into, you can see a lot of times I have 1880s or whatever, the rough decade, but there's work clearly going on before that as well. The idea here is we just want to get a general idea, a general sense of the flow of trends and events and their significance. So 1800, the battery came out of experiments done on animal electricity, how we can stimulate nerves in frog legs and things like that to get the frog leg to kick. And a person by the name of Alessandro Volta in Italy was able to do an inorganic version of that, and that became the battery. And the great significance of the battery was that now you could have the possibility of sustained electric current. Before that, you could certainly get electric shocks, and you could actually store electricity in jars. Really, they were called Leyden jars. Today we call them capacitors. Older term was a condenser. And, or just if you think about rubbing dissimilar materials together, you get that static electricity. So they had ways to store that, and you could shock people and other things with it. But until 1800, there's no way to get a sustained electric current. Once you had that, that opened up all kinds of things over the next 100 years. Also around 1800, the wave theory of light. What is light? What is it like? Well, Isaac Newton, the great British scientist of 1700s, well, really 1600s into the 1700s, we all know, of course, his theory of gravity. Because of that, he became the exemplar, really the greatest mind of the time. And throughout the 1700s, scientists looked up to him, and so they followed his lead on many things. And he had a theory of light as well. And his theory of light was similar to his theory of gravity in that it dealt with particles. That light were actually rays or particles of straight rays. So we're not talking about waves here, undulations, but straight rays, he called them, or particles. And he had a very sophisticated theory of how it all interacted together. It wasn't as successful as his theory of gravity, but of course, when you look at his theory of gravity, you say, well, Newton must be right about light as well. Well, around about 1800, the tide turned, as it were, and there are some experiments being done that, especially interference effects, and a person named Thomas Young sort of revived a wave theory of light that explained those effects. And light is one of the key things in the special theory of relativity, its nature and how it works, and so we'll be looking at that later on. Then in the 1820s, electromagnetism. What did we mean by this? Well, certainly people knew about electricity and they knew about magnetism, like compasses and things like that, magnetic needles that pointed north. They knew about magnetic materials. But in the 1820s, it was shown that if you have a current, okay, the battery, now we have sustained currents. If you have a sustained current through a wire and you brought a compass needle close to it, it was affected. It would change positions, change the direction it's pointing. So somehow, and if you turn off the current, it would go back to pointing north. So somehow the electricity through that wire was affecting the magnetic needle. So clearly there's a connection between electricity and magnetism. So this is the first time where you get the idea that you have electricity and magnetism as phenomena that are not separate, but they're interconnected somehow. Also going on about this time, you think, what are the railroads doing here in our story? Again, we will see more of that as we go along. But in the 1820s, 1830s, this is when the railroads were starting to expand from very localized areas, industrial areas, to actually carrying passengers much more out into the countryside, connecting cities, and so on and so forth. And this will be important for Einstein himself later on. 1830s also, electromagnetic induction. Well, we had electromagnetism here, the idea that electric current can influence a magnet. The idea of electromagnetic induction, and this will come actually, it's practically on the first page of Einstein's famous paper on the special theory of relativity. He cites some of the phenomena of electromagnetic induction. So what do we mean by this? If you take a loop of wire and you have a bar magnet, which obviously generates a magnetic field around that bar magnet, and you bring it closer to that loop, or actually even pull it away, turns out you generate an electric current flowing around that loop. So somehow that magnetic field, as you move the bar magnet back and forth, and in fact, if you just have the bar magnet stationary, it does not generate the electric current. So somehow the movement of the bar magnet and the changing magnetic field as it moves toward the loop generates a current. So therefore, not only does a current affect a magnetic needle, say, but a magnet, a bar magnet, can affect electric current. It can actually generate electric current or induce electric current in a wire. So that's what we call electromagnetic induction. The moving bar magnet induces a current in the wire. And of course, we'll be dealing with all of this in more or less qualitative terms as we go along. We'll get into a little more quantitative once we get to the special theory of relativity, but that's still a couple weeks away here. Okay, the telegraph. Well, clearly, if you have the battery and you can send electric current down wires, you have the idea, can I actually send signals using that electric current down wires? And so in the 1830s, of course, people had the idea before this, but in the 1830s, you start to see various designs for practical electric telegraphs. We're going to jump ahead now to the 1860s and 70s. It's not that nothing was going on in the 1840s and 50s. In fact, the handout lists some other things, but in terms of the highlights for our story, we'll jump ahead to the 1860s and 1870s now. Maxwell's equations. James Clerk Maxwell, great Scottish physicist, and what he did, he took some earlier work on all these electric and electromagnetic phenomena that people were discovering. The question is, how do you explain them? How do you come up with theories that make sense of them? And there's a fair amount of work done during that time. Maxwell sort of synthesized all that work and took it even further and showed that you can put it all together in a set of equations that described electric and magnetic phenomena. And one of the key results coming out of these equations, which was surprising and interesting, was that they predicted the existence of electromagnetic waves traveling through space. And in fact, those electromagnetic waves that the theory predicted seemed to travel at a speed very close to the known speed of light. And so the natural implication there was, or natural conclusion, was that that light was an electromagnetic wave. That electromagnetic waves traveling, according to the theory, about the speed of light. Therefore, seems like light itself might be an electromagnetic wave. And there actually were experiments done prior to this that showed light could affect electromagnetic phenomena as well. So it wasn't completely surprising, but it was just an astounding result in the sense that no one expected it to come out of these basic equations that Maxwell put together. 1860s, the telegraph was still expanding. There are telegraph cables, famous attempt to actually run a telegraph cable under the Atlantic Ocean. They started trying in the 1850s, failed several times. Finally, in the 1860s, they were able to get it to work. So a lot of technological development going on that, and also the expansion of the railroads. You may, in terms of United States history, about this time, you had the Transcontinental Railroad, actually sort of coming from the west and the east and joining together in Utah in the 1860s. And the telegraph and railroad, their expansion sort of were symbiotic. They went together because if you think about it, you have a railroad, of course. Often you'd only have a single track, and if you want trains running in both directions, you better have a good scheduling system and a good signaling system so that one train doesn't run into another. In fact, in many cases, they had accidents like that. And the way to do that was to string telegraph cables right along the railroads. And then you had to figure out a way to synchronize your clocks and so on and so forth. All of that comes directly into our story later on of the special theory of relativity. It also, this whole sort of connecting the world via railroads and also via telegraph cables meant, and synchronization of clocks meant or really spurred the development of time zones during this period, the later 19th century. Up until that time, the time was really regulated, obviously, by the sun if you're out in rural areas, but by the largest local city. And yet one city here could have a time that might be 15 or 20 minutes different from a city in another location. And so gradually you had the development, though, of standard time zones during this period. Okay, so that telegraph cables, expansion of the railroads. 1870s through 1890s, very roughly here, mechanical models. What's that all about? Well, going back to Maxwell's equations and the idea of light being an electromagnetic phenomenon, being an electromagnetic wave, waves travel through something. Water waves travel through water. They're an undulation. They're a disturbance in the water that propagates through it. Therefore, if light is an electromagnetic wave, or just the general wave theory of light itself, assumes that there has to be some sort of medium that light waves travel through. And especially in Great Britain during this time period, there was a lot of work done on can we create a mechanical model of how that so-called ether works, ether being the medium of transport for these electromagnetic waves, light waves. And they're actually very mechanical. They imagine gears and vortices and twists and turns and had very sophisticated mathematical analysis of these types of things. Whether they really believed the models were real in a sense that actually how the ether worked, or whether they were more like a scaffolding that you'd put together and then throw away when your model was done, so you just had the equations left. It's debatable. Some went one way, some went another way. But that's what the British especially were doing, British physicists and scientists. Interestingly enough, the French thought really the British in this were just going off in the totally wrong direction here. They derided their mechanical models. They said things like it reminded them of the factory system. And of course, throughout this whole period, you have the Industrial Revolution going on, actually even back in the 1700s, and Great Britain was a big leader in that with its factory model. And so the French looked at these physicists doing these mechanical models of the ether and said, that's ridiculous. It's too cluttered, too much like a factory, clanking factory, and so on and so forth. The French really prided themselves, the French physicists, that is, prided themselves on clarity of thought, rationality of thought, and it's very interesting reading obituaries, of all things, of scientists and physicists during the time, comparing the French and the British, because you can see what they lauded them for in the memorial. And the British often lauded their own kind for their creativity in coming up with models like this, whereas the French lauded their great French physicists who had passed on for their rationality and clarity of thought and so on and so forth. So, you have these rivalries, sometimes national rivalries going on here, but also sometimes just rivalries within a field of study. Okay, 1870s, 1890s, again, also, physics division of labor. What do we mean by that? Well, some of you may know or like to watch the television show, recent television show, The Big Bang Theory. And if you have, or if you haven't, on that show there's definitely a sort of a division, not only a division of labor, really, but a division of priority, a hierarchical division, I guess you could say. And on that show, who is at the top? It's the theoretical physicist, represented by Sheldon in the show. And below that, so the highest level of being, as it were, is the theoretical physicist. Below that, you have the experimental physicist. And below that, if you have a master's degree in engineering from MIT, you're not even worth being in the conversation. It's like you're an elementary school dropout, at least according to the show. And there actually is a kernel of truth in some of that, if you hang around physicists long enough. Go back, though, 120 years or so, it was totally opposite. It was the experimental physicists who were at the top of the mountain, as it were. And really, the whole idea of a theoretical physicist didn't quite exist at that point. It was just coming into being during this time period. And especially in European universities and German universities, you typically just have one physics professor who would run the whole, sometimes as an institute of physics, or the department there, might have an assistant professor, but that assistant professor was definitely subservient to the director of the institute, the physics professor. And is an experimental physicist who got those types of positions and essentially ran the whole show. At this time, though, you have the gradual development of the position of a theoretical physicist, somebody who certainly was trained in experimental physics, but focused more on the theoretical aspects of it. Now, it doesn't mean when I say experimental physicists, doesn't mean they didn't do theory. They did both. But now you have more and more where there'd be some who focused on experimental physics and others who focused on theoretical physics. The theorists, though, were still subservient to the experimentalists at this point in time. So you had this division of labor. Sometimes if a university was going to hire an extra professor, that assistant professor, they might choose somebody who was specializing more in theoretical physics, but it was the type of thing where it was still lower class in a sense. And this is the type of world Einstein was born into. So by the time he was ready to start his career, 25 years from 1879 when he was born, you had much more of a division of labor, so he could actually look forward to being a physicist who focused on theoretical matters versus experimental matters. Well, it doesn't mean he wasn't well-versed in experimental techniques and so on and so forth in his training. So, physics division of labor, Einstein born, 1880s. Incandescent lighting comes on the scene. Thomas Edison, of course, is working at this point. There are many other people. It was a fairly obvious idea. Once again, you have the battery way back here, and you have electric current, and you get a strong enough battery and maybe a small enough wire, you send current through that, what happens? It glows, right? And therefore, you can think, gee, if we could set this up right, we could get a strong enough current, get the right kind of wire that glows bright enough but also lasts long enough, then we have something. And it took roughly 70, 80 years for that to pan out. Edison himself, certainly he was able to come up with an incandescent lamp that lasted a long time and worked well after many attempts at it. But really his great innovation, his great genius, was a whole system of electric lighting. Not only just the lamp itself and how you'd create that and how you'd manufacture it, but also what about the wires, the switches? How are you going to power? How are you going to get the electric power there? Are you going to use batteries, or how's it going to work? What type of electric current are you going to use? There's actually direct current, alternating current, so all kinds of things went into this, and through the next couple decades, people were working those types of things out to see what was the best system. But that comes into our story because Einstein's father and his uncle were entrepreneurs in Munich, Germany at this time, and they set up an early electrotechnological company that specialized in incandescent lighting. And actually, in fact, at one point were awarded a contract for the Munich Oktoberfest to supply lighting for that, and so on and so forth. So that, again, was sort of the milieu that Einstein was born into. His very family was involved in a lot of the technological advances of the time, really the cutting-edge work at the time. 1880s, discovery of electromagnetic waves, going back to Maxwell's equations that predicted the existence of electromagnetic waves. A German physicist by the name of Heinrich Hertz in the 1880s confirmed their existence. And as an aside, that opened up a whole new technological possibility for sending messages not via wires, but a wireless messaging system, in other words, radio, which started almost immediately. Then in the 1890s, people started thinking about how to do that. And also, by the way, Heinrich Hertz, if we talk about megahertz for our computers, gigahertz, things like that. Hertz, our term for hertz, in terms of a unit of cycles per second, a frequency, comes from Heinrich Hertz, who was a brilliant both experimentalist and theorist, and unfortunately died at a very early age, in his mid-30s, before he could really have an impact on the physics world. But even the work he'd done up until that point, just discovery of electromagnetic waves and some other work he'd done, was very significant. Also in the 1880s, the Michelson-Morley experiment, which we will have a lot to say about later on. Here's the basic idea, though, a preview of it. If light waves are going to be traveling through the ether, this medium that pervades all space, if we think about this a minute, as the Earth moves around the sun and actually just rotates on its axis as well as it's moving around the sun, it's moving through this ether. And therefore, at the surface of the Earth, pretend we're moving that way through the ether, at the surface of the Earth, we should have an ether breeze in our face, just like if you ride a bike or something, you get the breeze in your face. And therefore, if you send a light beam against that ether breeze versus a light beam the other direction with the breeze, you should get a difference in speeds, and it should be detectable. Actually, it's a very difficult thing to detect, but Michelson and Morley had come up with an experiment to potentially detect it, and therefore they did the experiment. And what did they find? They found nothing. They found there was no ether breeze effect, no ether wind effect, which was a very surprising result. In fact, they thought they'd done something wrong, and many others who heard of the result said, this is terrible, okay, because all our theories seem to be wrong at this point. So, Michelson-Morley experiment, we will say much more about that and how we can explain that. Also in the 1890s, the electromagnetic worldview. This is sort of in contrast maybe to a mechanical model view, a mechanical worldview. The idea here was that maybe sort of the fundamental nature of the universe is electromagnetic. And using the theory of the ether and Maxwell's theory as well, we can actually sort of get to the really real, the basis of all reality, and maybe it's electromagnetic in nature. So some very sophisticated theories here trying to deal with things like the Michelson-Morley experiment and Maxwell's equations and some of the other things going on at this time. The electron itself was discovered in the 1890s and put it all together in a really what these days we might call a standard model of physics that's going to explain almost everything if we can. And again, some very sophisticated theories there. Einstein comes along about this time as well. See, 1896 to 1900, he was in college. Talk about that a little later on here. The important thing is that Einstein also came at some of these problems like the Michelson-Morley experiment, the nature of light, time and space, how that all works together. He came at it from a very different direction, though. Whereas a lot of the sophisticated work was dealing with this so-called electromagnetic worldview and how do you create a model of the ether, and electrons involved, and matter fits in there as well. Maybe even gravity fits in there. How does that all fit together? Einstein said, in a sense, that I'm just going to ignore that stuff. I have a different way of approaching the material. So we come then to Einstein, the final period here, 1900-1905, labeled Career and Life Anxieties. If you've read the Einstein profile, the profile of young Einstein, you hopefully got a good sense of that. In our next video clip, though, we're going to focus a little bit more on Einstein's early life here, and especially going up to the miracle year of 1905, and what was so miraculous about that, what was the nature of that miracle year, and the substance of that miracle year. So hopefully this gives you a good overview that provides the scientific and technological context for the world that Einstein was born into, and then what was trained in school. He studied essentially to be a physics teacher in college, and then we'll lead up to his miracle year, and of course, more specifically, the topic of our entire course will be one of the papers in his miracle year, which is on the special theory of relativity.